Before we start this week, I want to point out that we are not going to cover everything in the chapter on the face. Okay, so we're not going to cover all of chapter 17. We're going to cover the highlights, the things that I have found to be most important in clinical practice, but we're not going to go through everything, in part because there's a lot there, and it gets very complicated when you try to put it all together, and in part because this is the last week of class, and I don't want to add too much more before you go into the final. Likewise, we are not going to cover the two other chapters, 18 and 19, on the ears and eyes. The development of those systems is fascinating and important, but we really just don't have time. So please do feel free to read it in your own time. I'm happy to answer questions, but we're not going to go through it or cover it for this class. All right, so we will start this week with the skull and then move on to the structures of the face. So to begin with, we're not going to go through all of the different bones of the skull, but it's worth noting that you actually are born with more skull bones than you will have as an adult than you have now. And that's because the number of bones in the skull is going to reduce over time due to fusion of the sutures. So essentially, some of those bones that you have as a newborn will fuse to become single bones, and we'll talk about why it is that we go through that process. But the bottom line is that a newborn has 45 bones in the skull, whereas an adult really only has 22. So there's a large reduction in bone, although again we're not seeing less bone mass, just that we have fewer individual bones. All right, so by way of reminder, this is from several weeks back. There are two different ways that bones can form: endochondral ossification and intramembranous ossification. Endochondral bones are the ones that are formed by first laying down a template of cartilage, and then the bone develops from the template, whereas intramembranous ossification, those bones form directly from the cells from which they are derived. There's no cartilage skeleton first. If you need a refresher, we covered both of those types of bone development in the week that we covered the skeletal system. All right, so in the skull, and I've color-coded the words here to sort of match the colors in this picture. So the blue bones are the bones that are derived from intramembranous ossification. The purple ones are endochondral ossification. The neurocranium, okay, those are the bones that surround the brain, and they form from both mechanisms of bone development. So there's the chondrocranium, which is derived from endochondral ossification. That's your cranial base, so sort of that forms the base or the floor of essentially the brain case, I guess, is a way to describe that. The cranial vault, and if you think about something that's vaulted, like a church or a cathedral, that would be sort of what rises up and over, so the walls and the roof. That's derived from bone that's produced via intramembranous ossification. And you can see the different bones there. Again, you don't need to memorize them all. Also part of the neurocranium are the bones that surround the sensory organs, like your eyes, your nose, etc. Then you also have the viscerocranium, and those are the bones of the face and the pharyngeal arches. And we're going to talk about the face and the pharyngeal arches in a separate lecture, but they're shown in this picture in green. So again, we're not going to go through each bone individually, but I thought it would be worth going through the development of one bone, and by bone we're talking about the adult structure, although keeping in mind that in the newborn this will actually be multiple bones that later fuse. So we're going to go through one as sort of an example of how that happens, and then of course there are other examples in the book that you can read. Okay, so we're going to start with the occipital bone. So that's this one here, and again, multiple bones in a newborn, a single bone in an adult, and this is the bone that sort of forms the base and back of your neurocranium or your skull. Okay, how do we get it? So there's what are called the paracortal cartilages, and I've got them highlighted here in, not the best blue, but that's what we did, so we're going to roll with it. So the paracortal cartilages, they develop from the paraxial mesoderm, okay, and fuse at the midline and then become the basio-occipital bone, okay, so that's the base of the occipital bone, sort of lower down. Now keep in mind, if we're talking about bone that's derived from a named cartilage, and there are a bunch of them in the textbook, those are bones that are forming via endochondral ossification because they're starting with a cartilage template. So anytime you're reading through and they talk about, well, it comes from this cartilage or that cartilage, named after this person or that person or this location or whatever, that's all endochondral ossification. Okay? So the first part is we form the basio-occipital bone, okay, which is derived from cartilage templates. Then we have the ex-occipital bone that develops from occipital somites. So way back to the beginning we talked about somites. Well, here they are again. And this ex-occipital bone forms derived from the somites directly. Okay. Then we have what are called the periotic capsules, which are derived from what's called the otic capsule. At any rate, portions of those capsules are going to merge with both the basio-occipital bone and the ex-occipital bone, and they are all going to fuse to form the occipital bone. Okay? So all those structures are going to come together to form this one bone. Now, in the center of the occipital bone is a large hole that's called the foramen magnum, which incidentally means large hole. So, at any rate, that is where the spinal cord passes through and into the skull. So that hole is important. And in fact, if you have a narrow foramen magnum, you might end up with spinal cord compression, where the hole is narrow enough that it causes the spinal cord to be compressed, and that can cause damage to the spinal cord and interfere with function. But the foramen magnum is within the occipital bone. It's in the center and at the midline. Okay. Oh, and I missed some of my boxes. There we go. Okay. Again, lots of other descriptions of bone development in the book. If you have questions, let me know. This I thought was a good example, and certainly if you were contemplating potential exam questions, I would devote more attention to this one than to some of the others. Okay, so the skull, while composed of bones, and those are the parts we think about, also in a newborn composed of empty spaces, and there are two types, fontanelles and sutures. So remember that the cranial bones we talked about, they're unfused. They're sort of free-floating as much as a bone can be free-floating within the skull. Okay? Why are they not fused together into a solid protective structure the way they are in an adult to protect the brain? The reason, there are two. The first is that the the baby, the fetus, becoming a newborn, a baby as it's delivered, the head actually undergoes a great deal of molding as it passes through the birth canal. And that's important because the head is large, and the birth canal, while large, not as large as the head, as anyone who has ever delivered a baby vaginally is well aware. And so the baby's head actually undergoes a change in shape to allow it to fit through the canal. And that is mission critical, because if the head doesn't go through the canal, then the baby's not delivered. And in an era before our current modern medicine, that resulted in death of mother and baby. So it was very important that the head be able to mold. And that's why if you've ever been to visit a brand new baby, a lot of times they look like they've been in a bar fight and their head has got a cone shape, because going through the birth canal is not easy. But a couple days after birth, the head will have sort of resumed its normal appearance as the bones settle back into their usual place. And it certainly doesn't hurt the baby to have this sort of change in shape of the head. It's for the baby's benefit, and mother too. The other reason for this lack of fusion of the skull bones is because the brain grows very, very rapidly in infants and young children, rapidly enough that if the bones were all fused, very quickly it would fill the available space, and that would stunt growth and development. So if you've ever looked at pictures of young children or had young children, you'll notice that their heads are proportionally quite a bit larger versus their bodies than in adults. Their heads grow very, very rapidly, and then head growth slows as body growth continues, and you end up with more adult proportions. All right, so fontanelles versus sutures. This is sort of a wishy-washy definition, and honestly, your book doesn't make the distinction that I am used to making in clinical practice. So we're going to go with the distinction I've presented here because I think it's slightly more functional. So fontanelles versus sutures. Fontanelles are sort of the large open spaces at the juncture of several cranial bones. Okay? The key one, the one that you're probably familiar with if you've ever held a newborn, is the anterior fontanelle. All right? And that's this one here. That's the soft spot. So if you've ever felt the top of the head of a newborn baby or even a baby that's only a couple months old, as you run your fingers from the forehead sort of towards the back of the skull, you'll feel a depression, an empty spot where very clearly there's no bone underneath. That's the anterior fontanelle because it has not yet fused, and it takes a while for that to happen. It's also, in some cases, almost an early warning system. If it starts to bulge, you know there's been a buildup of pressure or something within the skull. So in babies that are ill or sick, bulging of that anterior fontanelle can be a sign that there's something going on. In reality, most of the time, it's just an area of the skull that has not yet fused, and it will. A suture, on the other hand, is sort of that linear space in between two cranial vault bones. So it's not a big open space, and you generally can't feel it if you touch the head of a newborn, although I don't suspect anybody's pushing too hard on the head of a newborn, or at least you shouldn't. But the sutures are the spaces in between two separate bones. Now, when we're going to the syndromes we're going to talk about in a couple slides here, the craniosynostosis syndromes, result from premature fusion of sutures. So I'm not terribly familiar with many syndromes caused by the premature fusion of fontanelles, I think in large part because you'd have to have premature fusion of a bunch of different bones to actually, fill in a fontanelle too soon. But sutures, in fact, with some frequency, and roughly 1 in 2,500 babies, at least one suture will fuse too soon. Okay? What happens then is that as the brain is growing very rapidly, it's expanding in all directions except the one closed off by the premature closure of a suture. And as a result, instead of getting a relatively round head shape, you get something else, depending on which suture it is that is fused. A lot of times, that is a sporadic condition and usually not a syndrome. Okay? In fact, it's relatively common. If you've ever seen a baby, and usually these are young babies wearing a helmet, a lot of times that's a baby that had premature fusion of a suture and they're attempting to correct head shape as a result. You can also go in and surgically correct them if need be. However, craniosynostosis can also be inherited. It can be inherited as an isolated familial trait. So everybody has craniosynostosis, or members of the family are at higher risk for it, but nothing else. And it can, of course, also be a syndrome, and we're going to talk about some of those. Okay, so in looking for anomalies of the skull to discuss, in reality, if you have an anomaly of a major skull bone, a lot of times that's lethal, and we're going to talk about an example of that. Because having properly developed skull bones is critical not only to the protection of the brain, but its normal development. Without them, you don't get it. So there aren't a lot of great examples of that, but we'll talk about one. And then we'll also talk about some craniosynostosis syndromes because those are less severe, consequently less lethal, and we see them more often. Okay, so we're going to start with something called acrania, which is exactly what it sounds like. It's a failure of the cranial bones to develop, the bones of the cranial vault. And so you essentially get a baby that does not have the cranial vault. The proper development of those bones is required for proper development of the brain. And if the bones aren't there, the brain doesn't develop properly. It sort of expands out into the available space in a way that it shouldn't be able to, and doesn't function the way that it should. Usually this is randomness. We don't understand a lot about what causes it, but it's rare enough that it's reasonable to assume that it's usually randomness. And you don't tend to see families that have had one baby with this that then go on to have multiple babies with it. It is uniformly lethal. And when talking about things in the area of prenatal diagnosis, certainly there's been a lot that's been out in the last 10 years or so, certainly over the period of time that I've been practicing, that's looked at some things that we have traditionally considered to be lethal and said, well, maybe we're missing some of the ones that aren't. This is not one of those. This is not one where there's a lot of debate about whether or not this might be viable in some cases. This is lethal, and pretty much always so. So I thought I'd go through a couple things here. So I'm going to highlight the bones that are generally missing in acrania, and it's these bones are the cranial vault, the frontal bone, the parietal bones, the occipital bone, which we talked about earlier. In terms of etiology, again, we don't really understand it, but in some cases, not most, but in some, it's an amniotic band. We talked a little bit about this when we talked about the placenta and the membranes, but you can actually have a strip of amniotic membrane that separates and then is free floating in the amniotic sac with the baby. And if it adheres to the baby, it interferes with development wherever it is that it adheres. So you get a lot of limb anomalies from amniotic bands, because that tends to be what gets wrapped up in it. You can get a catastrophic anomaly called limb-body wall complex, where the amniotic band wraps around sort of the abdomen or the trunk of the baby, and that's uniformly lethal, because you get just major anomalies of all those systems. And then you get, if it wraps around the head, you can get acrania. So that is one cause, but certainly not the most common cause. Also, a distinction worth making, this is not anencephaly. So we talked about anencephaly when we talked about spina bifida. Anencephaly is a failure of the neural tube to close, but at the level of the head rather than along the spine. This is not that. This is failure of the, again, of the cranial vault bones to form, which is separate from the neural tube. It's a different problem. So while these two conditions can occur together, and not infrequently do when they occur at all, they're not the same thing. All right, so here are some ultrasound pictures of acrania, and this is, again, I know you guys don't have a lot of familiarity with ultrasound images, but I'll try to talk you through it. The one on the top is sort of as if you were looking at the baby as it's lying on its back, and you're looking at it from the side, okay? So on the right-hand side of the image is the head, on the left-hand side would be the feet, in the middle you see the abdomen. And what you're seeing in this baby is on the right-hand side where the head should be, instead of that rounded head shape that's sort of outlined by bright white lines, and then in ultrasound, the bright white lines are the bones because they're very dense, they bounce back the most sound. You're seeing this sort of bulging structure coming out of the top of the head, and that's the brain, not contained by bone the way it should be, and sort of bulging out of the top of the head. In the lower image, you're actually looking at the face of the fetus head on, and so the two sort of the brighter circles, those would be the orbits where the eyes will be. Below them would be the mouth and chin. Above, you should sort of see a large sort of skull coming up off the top, a forehead, and then a normal skull coming off, and instead it sort of stops very short, and there's disorganized tissue on top that is, again, the brain. And then there's a 3D image of it as well. And in this case, you're looking at the baby head on, arms are sort of up near the face, and you can see the disorganized brain tissue there. It's important to note that the rest of the body of the baby develops totally normally. This doesn't seem to affect anything else. So when parents look at these babies, and I've included a picture that a family shared with a news organization of a baby with acrania that was born, the rest of the baby looks perfect and beautiful. And it's, in some ways terrible to see a baby with one problem that was so catastrophic that is otherwise perfect, but also for families reassuring to see a portion of the baby that is perfect. When dealing with a baby that has an anomaly that's so severe that the baby in some ways just doesn't look like a baby in the way that they're expecting, with the head the way that it is, sometimes it is of great comfort to see the parts of the baby that do look the way they expect. But a devastating diagnosis, no matter how you get it or what you do. All right, so we're going to move on to craniosynostosis, and there are lots of different craniosynostosis syndromes, lots of different sporadic causes of craniosynostosis. I'm going to focus here on the FGFR-related craniosynostoses. So we talked about FGFR and that family of genes in relation to achondroplasia. It's FGFR2. So we're going to talk about a couple different craniosynostosis syndromes caused by the FGFR family of genes. And again, they're fibroblast growth factor receptors, so they are involved in bone growth, which makes perfect sense. So the first one on the list here is Crouzon syndrome, and we're starting with that one because while it affects the skull development and the premature fusion of cranial sutures, it really doesn't seem to affect much else in terms of physical development of the baby. And they're focusing here on hands and feet because those tend to be associated structures with craniosynostosis syndromes. So you can see this child, and all of these children actually have a fairly similar look to their faces because they all have an abnormally developing cranial vault. And you can see that he's got sort of an unusual look with his eyes appearing to be sort of popped out a little bit. That's called proptosis. You can't really see his skull because of the picture, but you get the basic idea. The next one is Pfeiffer. So Pfeiffer syndrome, you see, in this case, you do see anomalies in the hands and the feet. So the thumbs are a bit unusual, as are the fingers, and the thumbs and the toes are actually both sort of very broad and shifted off to the side a little bit. And then finally, Apert syndrome, which we'll talk more about on the next slide. Apert, actually, you get fusion of the fingers and toes, so that they're actually, almost not functional. They're so fused. And we'll talk about it next here. So Apert syndrome is caused by FGFR2 on chromosome 10, and it's always a dominant disorder, but frequently it's a new mutation. So we don't see a lot of families where parent has Apert and then roughly half the children have Apert and so on and so forth. Usually it's a new mutation, and part of the reason for that is that it does go along with intellectual disability. It's variable, but up to 50% of children with Apert will have it. And until the advent of fairly modern medicine, the skull could not be corrected, and so these were folks who often did not reproduce. At any rate, so the craniosynostosis affects the coronal sutures, and that's what's shown in this picture here. So the coronal sutures, when you're looking at these skull pictures, the front is at the top and the back is at the bottom. So this would be a suture that would sort of run along the top of your head down to your ears, more or less. And so that's fused where it shouldn't be, and it produces this turi-brachycephalic head shape. What that means, okay, turris means tower, and the brachycephaly just sort of describes that fusion of the coronal suture. So in this case, because the skull cannot grow forward, okay, because of the fusion of the coronal sutures, you get this flattening of the midface, and you get growth of the skull sort of upward instead of forward. We talked about fusion of the hands and feet, and there are pictures here of what that looks like. They can be separated with varying degrees of success depending on how fused they are. You can also see fusion of the cervical vertebrae, so the vertebrae of the neck, which would interfere with normal rotation of the head.